was thinking it's probably easier if I just speak. Typing is weird. I got square root and squared mixed up. I didn't see it was square root, so I was trying to square them, which is obviously a mistake. So it should be the opposite way around, not this way. So I say if my say number itself check if we square the mid if it is x. Yeah, I know. I just wanted to try it a different way. Because then I can just do this, right? And then this should work. Wait, what's going on now? I feel like I'm missing something in the midsection. I think it's this part. Oh, yeah. It's the other way around, that's my bad. Yeah, okay. Because I'm coming through this way, I was trying to divide a potentially smaller number. So I was getting a fraction here when it should have been a whole number. I just wanted to do it differently to the way that I've done it before. Because I know any other time I've done it the way that you mentioned with the square, I think. Yeah, so here we get the square of the number itself. We're checking if it's equal to mid. Or if it's equal to x, then we just return it, and then it's basically a regular binary search that way. But I wanted to see if I could do it a different way. I think there should be another way of doing it as well that I want to try. I'm just trying out different variations. That's why I started with an easy problem. So okay. Okay, I guess I can move on. This one itself isn't that hard. Because I'm just trying out different binary search stuff just to cover the topic. What's here? Yeah, okay. I'll cover the next thing now. Yeah, I'm gonna take notes on this and then probably go to the bathroom. Sit. Oh wait, you did. Wait, which way? Alright, 6. I think I've done this too, but just haven't in a while. So say something like oh, okay, yeah. Okay, yeah. I think that's the way most people do it. I just saw that someone did it a different way, and I was trying to do it that way as well. So say 1, 3, 7, 6, 2. We want to find the highest value. I think that's what we're gonna do. So, if I remember this correctly, these questions are normally like the peak finding ones. Are the reason you can use binary search is that the first half is going to, or the first or second half will be monotonically increasing and then decreasing. So you can have it either way, and then you just have to find where it changes, which would be this point here, and then return it. We'll see. I'm going to keep going through it. So the peak is obviously 7. Yeah, so it would just be an extra conditional, right? So something like, we're gonna check, so let's make a comment, search, or rather, if I did it like this, it'd be to discern within the code. Let's say arbitrary array nums mid, it's less than nums mid plus 1. Means the peak's on the right side. So, else. Okay, I've definitely done this problem before, which is why I had some sort of idea of it in my head. But this is, what was it? leetcode 162. Yeah, definitely. I remember doing this. I just want to check the date. I haven't done it in about 5 months. Okay, that's fine. So I'll be back. I'll go to the bathroom. Where's my camera? Okay, I'll be back. Okay. A peak element is an element that is strictly greater than its neighbors given a zero-indexed array. Nums find a peak element and return its index. If the array contains multiple peaks, return the index to any of the peaks. You may imagine that nums -1 and nums n, so anything outside the array is negative in infinity, so anything outside the array will always be will always be less than anything inside the array. So we want this to run in negative, or we want it to be okay, so there can be negative values. But we just we just assume everything else is the absolute minimum. Okay, so first things first, considering all, we know that the array can't be null or empty, so if it is, we have a problem. So, and what's the value we actually want to return? I want to return an index. So yeah, we can just return anything outside the array. So if nums null, or the length of nums is 0, have no limits, or the -1, because that's outside the array. Then I guess the next thing I would do is get to a point where I'm comfortable. Like, where am I going from here? So if nums is null, say we still have to be in the array, so that would be 0. Right, we never know if we have the peak, but we still have to look for 1. Looking for the peak element, which I'm not sure if that means we're looking for an exact value or if we're looking for because we don't have a target value. So I guess that means we're just gonna keep sweeping. So it would be less than right. Mid calculation. Once we get to that point, we have mid. What happens beyond there? We have the number in the middle. Our middle point, we want to check. Yeah, we can't exactly just go ahead and be like, oh, do we have a target? We want to keep going. and maintain, I guess we have a value like peak is 0 or something, I don't know. The value itself, I don't know. Peak would be here dot I. We don't have it yet, right? So then if I said if nums mid is or like, are we just gonna end up returning what's at the left at the end after we cross over because we're finding the peak? But then again, we can have multiple peaks, so you never really know exactly where it's going to be. But we want to find like our largest possible value, and shrinking our search will lead us to the peak. I'm pretty sure if we do it the right way. So I guess I don't need this. What I should be checking for is if nums mid is what was the condition here that I saved? So if it's less than nums mid minus 1, so that means the peak is on the right. So we want to shift towards the right. So if nums mid is less than nums mid plus 1, the peak is on the right because nums mid plus 1 is bigger. So I would say left equals mid plus 1. It could be equal to the peak, I guess. Say right equals mid. And then maybe I'm completely off here. Yeah, there we go. I don't know if this passes all cases, but it passes the first two, which I'm happy with. We didn't get like it didn't give us a problem that has multiple peaks, but this one does seem to work. Let's go. Okay. That's good, that's good. Yeah, okay. That was good, that was good. That was a good solve. Yeah, so I understand peaks. That's fine. Let's see, was that on this list at all? Did I cover any of that? No. This is the next one I'll probably do. The next topic is, or the next pattern is searching on 2D matrices. So it's not much to cover. It's just a different type of search again. But yeah, making sure I'm aware of all of the patterns is what I'm looking forward to doing or trying to get better at doing. I think that works better or makes more sense. Just 1 second. Okay, we go again. Okay. Pattern 7. So let's say. I guess drawing a matrix should be easy enough. I don't know if I should use a. Yeah, okay, let's just. We'll just assume it's plain text. Let's go on. So. I could do some work to make it centered. It technically doesn't have to look a certain way. Go back like that. As good as it's gonna get. Okay. So given a matrix, in order to transform it, linear. Or we can transform. What do I want to say? Matrix positions, I guess. Matrix positions. To linear. See. So, for example. Something like 7. And we can index mapping like. So we do this by map positions. So this example, say yeah, since it's an integer, we won't have any like need to worry about decimals. Just getting a strict division. So main divided by 10 divided by 1. Is that double clicking? Right. Volume would be mid modulus for row. No, go. Yeah, the rows are the linear track we're going down. So for example, if we started off 6, 9, okay, so what number is going to be at the middle here? We want 4 on each side, so 9. 9's in the middle. So our first mid would be 9. And the index mapping of mid, or like 9, so row is going to be mid divided by its column. So, or divided by the number of columns, which is 3. So 9 divided by 3, we get 3. So 0, 1, 2, 3. Oh, that's wrong. 0, 1, 2, 3. I don't see why this would be picked as mid. Oh, we're doing indices. That's stupid of me. Okay, so 0, 1, 2, 3, 4. So we got 4. Mid is 4 divided by the columns, number of columns, which is 3. So we get 1. So row 1. And we want index 1. Okay, so column would be mid, being 4 again. 4 modulus of 3, we know the remainder is 1. So yeah, this is the position of 9. So that's how we're finding them. I don't know why I confuse myself in such a stupid way. But it's okay. It's okay. Talking through it is helping. Let's see. Yeah, that's basically it, I guess. We're gonna give it another go, or give it a go to begin with. So, leetcode 74. 74. Pretty sure I've done it at some point. Last time I did it was 2 years ago, so yeah, this will be interesting. Yeah, I'll get started on it when I come back. Bathroom again. Worst part about a heat wave is how hydrated you gotta be. So I'll be back. All right, I'm back now. Let's take a look at what is left. Wait, I'm just gonna fill something out real quick, actually. Okay, let's move on now. Where did this go? Cool. Okay. What else is there? Oh yeah, this problem. So you have a specific target we're looking for. We have, but this time we have X and Y to worry about. So that's like an extra level of complexity. It's been introduced. But from the notes that we wrote before, we know we have a way to kind of map them out into positions themselves. So let's say I guess then what would we define our left and right as? Would it be the first position in the actual top left, and then the right would be the bottom right? I don't know. We'll see. F matrix install or 0. Let's check happy in there. I guess I could just treat it like it's a regular, like, arrays problem, where we do 2D array. Or, no, we just use the flattening logic we had before. We say like an arrays problem, like a 2D arrays problem. Rows is the number of rows in the array, so matrix stalling, and then the call use length would be, or call use selected over call use is like the number of elements within any one of those arrays. So it's matrix 0. And then we can say that be 0. And then the number of entries we have. I thought someone was in the chat just now. We have say right can be equal to rows times columns. So let's say we have this array here. 4 by 3 is 12. So 12, well obviously we put minus 1 here. So this is the last element that we want to deal with. And now since we're searching for a specific value, because we have a target, we know that once we have a target in the binary search, we want to be able to know that even if they cross over, we want that last element or that last iteration to be included. So we know we're actually getting our target. So mid, we calculate the same way, always. left plus right left by 2. And then we have that calculation that we got from the notes to get the actual like index mapping. So we map the 2D array to be linear. So say row is going to be, separate them, so they're different concerns. Row can be, when I go back to my, like, where's my example with the array that I used? So I knew it was wasn't an even number, so it was easier to actually find the elements, but it's fine. I think it was mid divided by number of columns. So let's say this, for example, started 0 and this is 12 minus 1, so 0 and 11. So let's say 11 minus 0 divided by 2 would give us 5, because 5.5, but integer division doesn't include decimals, so we get 5. This is also 0, so 5, so 0, 1, 2, 3, 4, 5, so 11 is mid here. So 11 divided by our number of columns, 11 divided by 4, and integer division for 8 is 2. Wait, no. Mid's index, sorry. So index 5. So 5 divided by our number of columns is 5 divided by 4, we get 1, because yeah, we only get 1 clean division, and integer division would give us like 1.2 if we did that. So our number for the row is row 1, so we go down 1 row, and then the columns call would be mid, the modulus of columns as well. So then we get mid being index 5, modulus of 4, which also gives us a remainder of 1, so to go down 1, out 1 to get to 11, so we know that's right. So then we're going to say that our mid value will be matrix row all not calls. We'll change that. Now that we have our mid value, we can just check if mid value is equal to our target, not trigger it, it's target. We just return true, because it's in there. Else we need to check else if mid value is less. We need to adjust. Let's make this 1. Else it equals, right, equals mid minus 1. And then if we don't get there, we get false. Amazing work. Good job, me. Okay. This is in before I try to run it and get it wrong. Okay, never mind. We got it. Perfect. That runs in, I would say, O log m by n, because of the search space. Or is it still O log n because it's binary search? I don't know. It should tell me. I guess I can check. 1 analysis left. Or rather, I'm smart. I would go here. because I think I can do more than that here. Oh, wait. Oh, no. I'm sorry. It should copy over, right? Or does it not let you copy? You're not able to copy from the editor anymore? Or maybe it's like a counter for cheaters in contests. Never mind. I'm just making stuff up. Okay, let's see. So show me the complexity. Upgrade a pro. Not happening. I guess my one and only hope now is to ask an AI. I'm expecting okay by n is the complexity of log by n. Yeah, okay, I'm right. Okay. Yeah, okay. Do I keep going? Because I am kind of on a roll. I guess maybe. No, not really, but like I'm having fun, at least. I'm learning. And I do want to finish binary research before the end of the day. So I might as well keep going. I'm just getting kind of hungry. Okay, so binary search and greedy. Binary search and prefix sum. I guess these last three are kind of nice to have, so they're not really important. I guess I'll give them a go. Because they are kind of the same as the predicate searches from before, when we're checking like true false values, but you just kind of have to write a helper function and then check and then do your binary search. So it's not really the binary search itself that is the hard part. It's like when you're given the problem, are you able to solve it? Or are you able to see that you can solve it with binary search? That's the issue. Like getting that like mind frame around it, I guess, is hard. Okay, I'll give this one a go, and then we'll see how we go. This is a new approach for me for learning DSA, because normally I just cram before I need them, and I feel like that's impacted my learning, because obviously I still learn, but I just feel like it's not as efficient because there will always be issues with retention if you don't keep it up. Okay, so pattern 8 is combo binary search and greedy. Let's move this up. Going away. All right, let's go. Oh, apparently it's very common. It's a very common pattern. So, because I'll just only include the example. Example. It's a problem called aggressive cows, but I don't think that's on leetcode. I can check code aggressive. Okay, so aggressive cows or another magnetic force main vehicle, which is leetcode 1552. Okay. Let's continue note taking. Say we're given a sample input. So we're given Java, or no, let's ignore. This could be any language. So we'll say stalls is equal to 1, 2, 4, 8, 9. Is equal to 3. Maximize minimum distance. That's the goal of the problem. Okay, let's say the goal is to maximize minimum distance. I hate how leetcode or DSA competitive programming problems try to trick you with language, because instead of saying maximize minimum distance, you could just say reduce the distance, you know, as much as possible. But I guess using maximum and minimum right after each other is kind of like wordplay to mess you up. Okay, so the issue now is that I don't actually know the problem statement. Okay, so core task is to distribute m cows into n positions such that the minimum distance between them is maximized. Okay, we're supposed stalls cows. So the distance between them is the distance between the greatest and the largest. We get the actual distance, we just subtract them. We're able to check, can we actually position okay, so I should do this the other way around. So search. What is this? Why does that stay there? Okay, so I can't have the map picture. That's kind of stupid. Search on answer. So something like distance. Distance between. One dot. Okay, that works. Okay, we have our distance. We want to check. Check. Greedily, can we place? So we're gonna have some north. Do this again. We have some private functions, so private boolean and place. Can we place it? Who knows? Say in distance. Haven't confirmed whether we can have decimals or not, but or floats or whatever, but should be good for now. Check quickly. And our monotonic is if distance too large. False. Smaller. Because we're trying to shrink this, get the minimum possible distance between them. Okay. So magnetic force between two balls seems to be the problem that we're trying to solve here. So I'm going to queue that up. And if this one is one that we struggle with or take too long with, I think I'll stop it there. Maybe do the last two patterns on my own. I do not remember solving this at any point, so it was probably 2 years ago. Probably some time ago. And I don't even think I solved it with binary search. It's, if I think about it, I feel like it was either stacks, queues, or something else that I used to solve this. Or probably just sorting. I can't remember, but let's see. Yeah, 2 years ago. So it might be binary search. I have no idea, but I don't remember solving it. Okay. It's getting hot. It's getting hot. Let me check the weather. Oh, it's 25 degrees Celsius. So it's 77 degrees Fahrenheit. Okay, so absolute distance, don't care about that. It's just going to be, actually, we obviously do care about the absolute distance, but I'm just saying it's, we don't care about the implementation because it's simple. It's just going to be math.abs of x minus y. So within here, we're just going to keep our can place, and then some sort of distance as well. So isn't binary search just inherently greedy? I mean, at times it can be, I guess. I guess, yeah, it's divide and conquer. Greedy's more like aggressive, because it just tries everything, but we do the greedy within our helper. So the greedy algorithm will probably be in here. And we're not told whether we have a monotonic decreasing or increasing, like it's not explicitly stated. So we probably have to sort them. But first, we'll say if position. No. I'm gonna take this off, it's too hot. Okay, so max distance we can get if we have nothing, or minimum magnetic force. Yeah, so we want the minimum distance to be maximized, but this function name is so stupid. Minimum distance maximized, so what would be the maximum? Yes, we could return -1, but we're also not confirmed that the values. Okay, we've confirmed the values are always going to be positive. Okay. So we can return Okay, this is probably my last problem. So I'm checking the live stream. Okay, let's get this solved so I can end the stream. Okay. I'm not sure about the greedy though. I know it's gonna be very distance against this. We don't actually know it's the min distance, but we want to know, can we place or it's possible. We want to know if it's possible to distribute a ball into a basket at a given distance. Okay, that's what we should be worried about. Oh, okay. So let's say that we sort. Where's that sort? It's gonna be lowest to highest. So position and solve, and then let's say that it's. I say min distance or just distance. I'll just call it distance. Initial distance is absolute. X minus y, so that would be positions. I still need a left and a right? So left is 0 equals position. equal to m, the number of balls we have. So we need that here, 100%. Well, we're doing it based on answer, so see well, I'm still confused on what they mean by minimum distance because couldn't they just have, like, because I feel like, I see, such that the minimum magnetic force between any two balls is maximum. So I guess it means like we want to maximize the number of the distance between all of them, but we don't actually want to use the minimum value. So like obviously we could just say, oh yeah, it's 1 in between all of them, and it would be fine. But I think we want to actually increase them. So I guess, yeah, we can't use 0. It has to be 1. And then whatever we have here should be in this position. Right, so then I'll lift, looking for a specific value. We don't necessarily have the target yet, but yeah. Mid always the same. Alright, right to left. Go to, and then this is where we need it if it's possible, but we don't have that written yet. So what we should know is for this to be possible, mid is our min distance. We have our minimum distance that we're checking now being would be 1, right? Or yeah, but in the case of the algorithm would be mid. So let's say we have its or the array position, our number of balls m, and current min distance. So when we're dealing with the problem, how many balls have we placed? So this is like not Coco eating bananas, but there's another problem similar to it, where you have to find the number of days that something happened. I mean, yeah, it is Coco eating bananas as well, depending on how you solve the problem. But yeah, so let's say, no, I'm thinking of bananas now. The number of balls we've placed. Always start at 1. Then we need to keep track of the last one we placed so we can check the distance between the two. So let's say int last placed would be position 0. So that's like our starting point, our sentinel. Okay. Then we can loop over position. So while we're going over position for int I 0, position, so we need the watch. We want to check if we're far enough away. Can we continue? So let's say if position I minus last place. So if the distance between these two is greater than or equal to min distance, then we can place another one. And then obviously we update last place. Position I. And then if we can't do it, we return true. So once we've reached multiple points, it'll say if placed equals m, we return true. But if we can't do it, we return false. Okay, so then beyond that, okay, we get to the point where we can actually solve this now. So we just want to check if we were able to actually do this, then we do it. So if can play, or if it's possible, position min distance right now is right, or what, or whatever no, we're taking a midpoint between left and right, and we decided that would be our starting point. So if we can do it, you know, we can place it at mid. Mid is safe. So answer. So our initial answer should be current magnetic force. So let's say answer equals mid, and we want to try a larger force. So it's mid plus 1. Otherwise we can't do it. So, right, it's mid. And then here, okay, where did I mess up? Wait, what's wrong? Oh, yeah, okay. Position left and then position. Right. So because of no, off by 1. Maybe. See, I don't know why that's giving me a problem though. Because this is obviously working. It's giving me the right answer. I'm just gonna ask him. I'm really tired right now. I know I shouldn't do this, but checking. Oh, okay. Makes sense. Left is 1, so it should be, yeah. Yeah, okay. That makes sense. Okay. I'll take that.